Swayam Prabha. Digital India. Educated India.
Hello everyone, today is the second lecture of this week. So in this lecture we will analyze a plain truss using finite element method. We will take a small problem, relatively simpler, which has less number of degrees of freedom so that manual calculation is feasible, and try to find out the displacement, member forces, reactions using finite element method, and through this process we will also try to comprehend the various steps involved in FEM. So this is the problem we will take, but before we start solving it, let us just quickly review whatever we have discussed in the last class. This is the element stiffness matrix written in local coordinate system, we know, and this local coordinate system element, the matrix can be represented with respect to global coordinate system through a transformation matrix, and this is the transformation. Now, then we also, if you substitute this transformation in this, then finally we get a global stiffness matrix like this, where lambda x, lambda y are the cos alpha and sin alpha. Please note the alpha is defined like this. So when we write this stiffness matrix, our starting node number 1 is this, starting node is this, and then end node is this one. So your starting node is this, end node is this, and angle alpha is defined like this. So if we have to write or express the element connectivity, we will say that this element E is connected between node number 1 and node number 2, not the other way. If we define the connectivity like this, node number 2, node number 1, then this will be our starting node and this will be our end node. Then alpha needs to be defined accordingly, and then U3, U1, U2, U3, U4, these also will change. Okay, so this is very important. Now, so once we have this stiffness matrix with respect to the global coordinate system, so similar exercise we can also do for load vector as well. So this is the load vector, and you see, this Fe includes both. If you have a distributed forces and if you have a concentrated load, concentrated moment, includes all forces, all external forces. Now, if you have a concentrated load, that's what kind of load we have in truss, then this can be written like this, and when we implement it, we will see that we'll try to represent the forces directly with respect to the global coordinate system, and in that case we do not have to apply this step. Like, for example, if you have inclined load like this, it can be distributed like this and then directly using the load vector. So final element equation will be like this, and Ui are the load vector, element level displacement vector, these are the element level force vector, and lambda x, lambda y are defined like this. So this is the element equations we know. Now let us apply this. So this is the problem. Now you see, we know these are the steps involved in finite element method, but the method that we will, for implementation point of view, these steps we will discuss today. Post processing will not discuss today, because today our objective is to learn the steps involved in solution. Once we get the solution, once we have computer code ready with us, we will see the post processing as well. So this is we will do now. So the first step is discretization. As we have seen, the first step is the discretization of the domain. So domain means in this case we have just 3 members, right? So here discretization means now we have 3 members, means we have 3 elements. So this is, now we have, let's see, before we discretize it, we have to do some node numbering and element numbering. So this is the problem. This is the truss. So we have to, this is element number 1, this is element number 2, and say this is element number 3. You can give this as 1, this as 2, and this as 3 as well, but we have to follow some element numbering, so I am following like this. Okay, but having said that, we will see when we solve larger problem, how you number the system, how you number the node, how you number the element. That's also very important if you look at from the implementation point of view, if you look at from the computational efficacy point of view. So node number 1 is this, node number 2 is this, node number 3 is this, and then these are the degrees of freedom. At every node we have 2 degrees of freedom, and 1 and 2 when we write, this is the global degrees of freedom. Okay, so globally in this problem we have 6 degrees of freedom. First degrees and second degrees of freedom is at node number 1. Similarly, at node number 3 we have 3 and 4, at node number 3 5 and 6. So total 6 degrees of freedom we have. Now, so what are the information we have about for this element? Information is, just now I was saying that connectivity, how you define the connectivity, that is important. Now you see this table gives you the information about the node and the information about the connectivity, how the elements are connected between nodes. So element number 1 is this, element number 1 is this, and this element number 1 is connected between node number 3 and node number 1. So this is our first node for element number 1, and this is our second node for element number 1. Element number 2, and what is the angle alpha for element number 1? Alpha is 60 degree. Similarly, element number 2, it is connected between 2 and 1. So this will be the first node for element number 1 and the second node element number 2. But again, this is how I have taken. If you wish, you can take the connectivity between element number 2 as 1 and 2 instead of 2 and 1. You could have taken 1 and 2, but in that case, if we define the connectivity at 2 and 1, our angle will be this, because this will be the starting point. Angle will be 120 degree. But if you define the connectivity as 1 2, means this is our first node and this is our second node, this angle needs to be defined properly. Okay, so element number 3, this is connectivity between 3 and 2, node number 3 and 2, and the angle is 0 degree. Okay, and the properties for this truss problem, for all the members we have uniform properties. A is the cross sectional area, E is the Young's modulus, and L all the members L is same. Okay, so now so let's now discretize it. So this is the discretization. Discretization means take all the members separate from the system. Now that's what I was just mentioning. This element number 1 is connected between 3 and 1, and 3 is the starting node and 1 is the second node, and that's why our degrees of freedom are at the element level. Degrees of freedom is defined like this. This is U1, U2, and this is U3, U4. Element number 2 is connected between 2 and 1. That's why this become 1 and 2, and this become 3 and 4. Element number 3 connected between 3 and 2. This is our starting point and this is our end point. That's why this becomes 1 and 2, and this becomes 1 and this becomes 3 and 4. Let's take first, this is step 2 element equation. Let us take the first element. First element is this, and what is this? Is the equations this is the equation we know, and then if we substitute lambda x and lambda y, we'll get an equation like this. So this is for element number 1. Okay, now in this equation, if we just divide it like this, then this block gives you the interaction between node number 3 and node number 3. This gives you interaction between node number 1 and 3. This block gives you interaction between node number 3 and 1. This gives you interaction between node number 1 and 1. Okay. Now this was for element number 1. Let's do the same exercise for other 2 elements. For element number 2, just substitute this lambda x, lambda y in the equations. This is for element number 2, and similarly for element number 3. Element number 2 also, these are the nodes. When I say 2 1 2 1, these are the global nodes. Okay, Similarly, this is for element number 3, and these element number 3, the global nodes between this element is connected is 3 and 2, and this is how the interaction between these two nodes given in the stiffness matrices. So this is element equation. Now these are the summary of the all the now we have done step 2 is done. We have the element level equations for the all the member, right? Now next step is, once we have this information, next step is we have to assemble this. All these element level equations need to be combined to get the global equation. Let's do that step. So step 3 is the assembly of element equation based on element connectivity. This is very important. Now there are two important criteria to be satisfied. The first criteria, when we assemble them, first criteria is, you see, when we wrote this element level equation in the discretization step, first step, we divided the entire domain into small elements, right? Now it is the time to again join all these elements. Now when we join all the elements, certain constraints, certain criteria to be satisfied. The first important criteria is the inter-element connectivity. Now elements are connected through the nodes, right? And as we discussed at the very beginning, first the information will pass from one element to another element through this node. So at this element, at this junction, at the inter-element continuity should be mentioned. In this case, the primary variable, which is called displacement compatibility, means before I'll tell you what is displacement compatibility in the context of this problem and how it is to be ensured, let us see what is another criteria. Another criteria is the inter-element equilibrium of the secondary variable, means force equilibrium. And if you recall, these are the two criteria you have used in solid mechanics, you have used in elasticity, you have used in structural analysis, you have used in matrix method of structural analysis. These two criteria are so fundamental. The equilibrium needs to be satisfied and the compatibility needs to be satisfied. Okay, compatibility within the element is already satisfied, because that is how you define the field variable or variation of the field variable over an element through a shape function. But now it is the time to maintain connectivity between two elements, compatibility between two elements, equilibrium between two elements. Okay. Now, what is a displacement compatibility? You already know what is displacement compatibility. This gives you, just to help you to visualize it, it says that, you see, if for instance in the context of this Truss problem, in this node, we have two members are connected, but then when the deformation takes place, the deformation should be such that there is no discontinuity at this node. Okay, this is to be maintained. Similarly, here in this problem, if for two-dimensional problem, we will be starting probably in the next week. We will start. We will see that if discretized by two-dimensional element like this and it is undergoing deformation, the deformation should be such that there is no discontinuity created like this, unless otherwise there is a crack or fracture in the material separation takes place. But those things, those phenomena need to be dealt with separately through some special technique. Okay. Now this is the displacement compatibility. Now let us see how it is to be ensured during assembly of the element. So these are the elements, and this is the when those elements are connected. Okay, this is the system as a whole. Now these are the local variables. When we write these all are local variable, right? Variable or with respect to element level. Okay, and U1, U2, U3, U4, these are all global variable. Now the compatibility says that, you see, at this joint number 1, at this joint, if this joint we have deformation, say from this element at this joint, your displacement is this, and from this element at this joint your displacement is this. Now if the continuity to be ensured at joint number 1, at the node number 1, these two displacement should be same, and these two displacement should be equal to the displacement U2 here. Similarly, if we see that node number 2 horizontal direction, if we take this member number 2 at node number 2 displacement is this, and from member number 3 at the same node number 2, your displacement is this. But then at the node number 2, if the continuity needs to be maintained, then this should be equal to this, should be equal to U3. That needs to be ensured at every joint, at every node, right? Now, let's see that. So, take node number 1. At the node number 1, just now I said, so if we take the continuity, if we consider degrees of U1 degrees of freedom, which is the horizontal displacement here, then this criteria needs to be satisfied. Okay. Similarly, at the same node, if we take the other direction, y direction, then this criteria needs to be satisfied. Similarly, if we take node number 2, at node number 2, similar criteria needs to be satisfied. This is for the horizontal displacement in this case, and similarly for vertical displacement, and the same condition can be written for node number 3 as well. Node number 3, it is for horizontal displacement, this is for vertical displacement. So these need to be ensured. That when this is ensured, the compatibility, the continuity between element or the inter-element continuity is satisfied. Okay, now the continuity is satisfied. Now next part is we have to satisfy the equilibrium of forces. Now look at these two diagrams. The first one shows the forces at the element level, and the second one, this one shows the forces the global level. So P is the external force, and H3, V3 and V2, these are the support reactions. The equilibrium says that external force and internal force, they should maintain a balance, right? But when a body is in equilibrium, at every point of the body should be in equilibrium, right? And so when we are assembling this, when the different elements at the joint, at the inter-element junction, this equilibrium need to be maintained. And what it says is, look at this element number, look at joint number 1, node number 1. Now, node number 1, the forces, let's take the force in horizontal direction. Now, from element number 1, we have force this one, and from element number 2, at the same joint, node number 1, we have force 3, this one. So, then what will be the total force at node number 1? Total force at node number 1 will be Q31 plus Q32. Now, this is in this direction, right? Now, let's see in the other direction. At node number 1, force is this, and the node number at node number 1 from other element, force is this. Then the total force will be Q41 plus Q42. This should be in this is in other direction. Now compare these forces with the forces we have here in this free body diagram. Now at node number 1, we do not have any force in this direction. This force is 0, and therefore this should be equal to 0. At node number 1, we have force in vertical direction P acting downward, so this force should be minus P. So if this is satisfied, then the equilibrium at node number 1 is satisfied. So the similar condition need to be satisfied at every node number 2 and node number 3. Let's do that. So write those equations. So for node number 1, we have already written this is the first equation, this is the second equation. Similarly for node number 2, this is the first equation and this is the second equation. And node number 3, this is the first equation and this is the second equation, right? So this is the equilibrium condition. These equilibrium condition need to be satisfied. Now we know the condition, the compatibility condition to be satisfied at the inter-element, in this case at the node, and then the equilibrium condition to be satisfied at the node. Okay. What we have is this. This is our global load vector. Global displacement vector we know. Okay. And this is the global load vector, and this global load vector we already have seen. These global load vectors are this equilibrium condition, and this is our final equation. Ku is equal to F, the and K is the global stiffness matrix. Now we need to determine what is the global stiffness matrix, right? Now, so these are the equations we have for all these all the elements, right? Now, and we also know this is the compatibility condition. Now let us now these stiffness matrices written, you look at this these expression, these variable, the degrees of freedom, they are written with respect to the degrees of freedom at the element level, degrees of freedom at the element level. But then the compatibility condition tells us that how these degrees of freedom at the element level related to the degrees of freedom at the global level. U1, U2, U3, U4, these are the global displacement, Now what we know, since we know these equations, let us substitute these degrees of freedom in the equation itself. If we do that, so these equation become this. So this becomes this from this equation. Similarly, this becomes this, and then finally for element number 3, this become this. And if we substitute this in the vector, then we have now this vector. So these vectors are written. These are written with respect to the degrees of freedom in global coordinate system. Though the forces are still written in terms of with respect to the element level. Okay. Now, next what we do is, this means what? This step is important, and this numbering is also very important. What this numbering tells you? This numbering tells you, okay, this numbering tells you that this is 5612. 5612 means, if you remember the structure was like this, and this was 1 2 1 2, this is 3 4, and this is 5. These are 5 and 6, right? And this was our element number. This is our element number 1. This is our element number 2. This was our element number 3. Now, this tells that element number 1. This is now this is the 5 6 1 2 are the degrees of freedom, and then corresponding columns are these 5 6 1 2. It means that these gives you this 5 5. This gives you the forces in this direction, means which is Q11 due to the displacement 5. This is the degrees of freedom 5. Now this gives you the forces in this direction due to the degrees of freedom 6. This gives you the forces in this direction due to the degrees of freedom 1. That's why it is 1 here. And this gives you the forces in this contribution of the forces in this direction due to the degrees of freedom u2. That's why 2. So total force will be this contribution from each component. Similarly, for all other equations, we can write. Now, similarly, we can put the numbering for stiffness matrix, numbering for the element number 2, and then numbering from element number 3, 5, 6, 3, 4. This is next is the equilibrium, right? Now, we need to satisfy this equilibrium condition. All these we have just written this equilibrium condition now. Now, these equilibrium conditions now need to be satisfied. Okay. Now, let us satisfy this equilibrium condition. Let us see the first equilibrium condition. First equilibrium condition is this. So, it says that this Q31 we have here. This is Q31, and then plus Q32. Q32 is Q32. This should be equal to F1, right? Now, just now we mentioned that Q33 is what? Q33 will be this entire row multiplied by this displacement vector, and similarly this Q33 will be this entire row multiplied by this vector, and this should be added, and once we add it we will get F1. Now, so if we do that exercise, so this is for Q31 and this is for Q32, and let us substitute this in this equation. If we do that, this will be Q31 and this will be Q32. So this now this will be Q32. Let's now this is our first equation. We have this is now initially we know our total 6 degrees of freedom, so our stiffness matrix we don't know what are the entries in the stiffness matrix, but we only know the stiffness matrix will be 6 by 6 matrix. So let us start with 0, and then we'll populate as we keep on satisfying the equilibrium equation. We will populate this stiffness matrix. We'll populate this stiffness matrix by writing U1, U2, U3, U4, U5 global vector like this. We have already satisfied the compatibility equation. Now it is the time to satisfy the equilibrium equation and get the final global equation. Now, what we have in this from this equation? Now, in this equation, you see, we have the first row in these two equations will give us the first row of our stiffness matrix. Now, this is Q. If we add this one and this one, what we have is we have you need to on U1 will be multiplied with 1 by 4, and here U1 will be multiplied with 1 by 4, right? So first entry in this it is corresponding to U1. This is corresponding to U1. This is corresponding to U2. This is corresponding to U3, this is U4, this is U5, and it is UC. This is how we multiply with this entire row and this load vector, this displacement vector to be multiplied, right, to get this. Now, E1, the contribution of E1 will come from this equation and will come from this equation. From this equation, the contribution will be 1 by 4, and from this equation, the contribution will be 1 by 4. So the total contribution of U1 will be 1 by 4 plus 1 by 4. Right. Now, let's do it for U2. U2, the contribution of U2 will be from this contribution will be minus root 3 by 4, and contribution also here, this is root 3 by 4, and this will be minus root 3 by 4 plus root 3 by 4. Then U3 is this. U3 we have U3 here, and this contribution will be minus 1 by 4. In this equation there is no U3, so total contribution will be minus 1 by 4. Then U4 is here, the contribution will be this, and then there is no contribution from this equation, contribution is this. Then U5, the contribution is minus 1 by 4, there is no contribution here, minus 1 by 4, and then U6 finally minus root 3 by 4, there is no contribution from this equation, minus root 3 by 4. So this will give us the first row of global stiffness matrix, okay, and this first row of global stiffness matrix when multiplied with the global displacement vector, it will give us the first equilibrium equation, right? Now, same exercise we can do for other equilibrium condition as well. Now, let us do that. Now, let us do it for F2. If we do it for F2, then corresponding rows and column will be this. Here we have this is F41 and F42, F41 and F42. So these two equations need to be added, okay. Now, let's do that. So this is the equation, same thing if we can do, say for instance, first the contribution of U1 will be here minus root 3 by 4, and contribution of U1 will be here root 3 by 4. So this will be root 3 by 4 minus root 3 by 4. U2 contribution will be 3 by 4, and again 3 by 4 plus 3 by 4. U3 contribution will be this. This is U3 contribution. U4 contribution will be this. This is U4 contribution. U5 contribution is this. This is U5. U6 contribution is finally this. This is U6 contribution. So, and then this is our second equation. Same way, when this row, the second row of the stiffness matrix multiplied with the global displacement vector will give us the second equilibrium equation like this. Now similarly we can do it for other third equation as well. For the third equation, these will be the corresponding equations in different element, and if we substitute this, we will get this expression. The same thing, same exercise we have to do for all equilibrium equation, and if we do that for all equilibrium equation, our final stiffness matrix will be this, and this will be our total, this will be our the global stiffness matrix. This is global stiffness matrix and this is our force vector, right? Now this equation now need to be solved. Now, so this is global stiffness matrix, this is global displacement vector, and this is the external forces, and this is the unknown reactions, right? Now next is imposition of boundary condition. Step 4. Imposition of boundary condition means if we have any information about the boundary, that information need to be put there. Okay, we have to tell the solver, we have to tell the equation that these are the conditions at the boundary of the problem. So when the equations are being solved, these conditions must be satisfied. Okay. Now what are the conditions we have? This is the equation. Now we have final equation, global equation. Now what are the boundary conditions we have? You look at the support condition. If we see that at the support at node 3 we have hinge joint, at node 2 we have roller joint. So naturally U4 will be 0, U5 will be 0, and U6 will be 0. So these are the information we have about the boundary. We don't know about U3, we don't know about U1, and we don't know about U2. These three displacement U1, U2, U3 are to be determined. Okay. Now, so if we substitute this in this equation, so these U4, U5, U6 will be 0. So our final equation become like this. Now in this equation you look at how many unknowns we have. We have actually 6 unknown. U1, U2, U3 are 3 displacement unknown displacement we need to determine, and then V2, H3 and V3, these are 3 reactions. These 3 reactions we need to determine. It is a linear equation, 6 unknown and 6 equation. Okay. Now after imposing the boundary condition, once we have the final equation, now we are ready to solve these equations. So next step is the solution. Okay. Now how to solve it? So first let us see some information about displacement known and some information about the forces unknown. Our primary variable in this case is displacement, so we have to find out displacement first, and once we have the displacement, with the known displacement we will find out the forces. Okay. So in order to do that, we have to do some partitioning of the matrix. Okay, here our life is easy because all the unknown displacement U1, U2, U3 are one side and all the unknown forces are other side. But if we will see for some other problem, because of the numbering, if we do not have the known displacement like we have here, U1, U2, U3, then we have to do some condensation and then separate it out. We have to bring all the known information together, and we have to bring all the unknown information together. Okay. And in this case, that exercise we do not have to do separately, because the way the numbering was done, the way the displacement, the boundary conditions are in the structure, it is already there. Okay, known information is one side and unknown information the other side. Now, suppose if we what we will do now, we will just rewrite this equation like this. Okay. Now what it means? It means that U stands for unknown displacement, and UK stands for known means known displacement. FK stands for that known force, and FU is unknown force. Okay. And these blocks are written like this. So, this is K K U, this is K K K, this is K U U, this is U K K. This is just to understand how we will be how we will be solving this equation. Okay. Now, from this, what it will give us? It will give us two equations. First equation is this. This will be the first equation. This will be the first equation. Now, in the first equation, you see stiffness matrix anyway we already have. In the first equation, only displacement is unknown and force is known. So, this is our first equation. Okay, and then the second equation will be this. In this case, so once we calculate this value, this UU, then we can substitute UU here, and then we can find out what are the unknown forces. Okay, so this first equation will help us to determine unknown displacement, and the second equation will help us to find out unknown forces. Okay. Now, next is next, let us solve it then. So, this is our first equation, and if we write the first equation, this our first equation, then if we solve it, and then this will give us U1, U2, U3 are this. Okay, and once we have U1, U2, U3, then you apply the second equation. If we take second equation become this. Already you have determined U1, U2, U3. If we substitute U1, U2, U3 here, and then this will give us the unknown forces. Reactions are like this. Okay. Now these are the unknown reactions. So we have determined the displacement, we have determined the unknown reaction. Now only one thing is left, is to find out the stresses in the member, in this case the forces in the member, or the member forces, the element forces. Okay, let us do that. So next part is the finding the element forces. Okay, now look at this, the truss member, where the forces and displacement degrees of freedom are expressed in terms of local coordinate system. And you recall that in this case, if you see that we discussed, since in truss member your force is always along the length of the member, force is always axial. So this is anyway 0, this will be anyway 0, and the axial force, the member force will given by this. Okay. So if we take the sign convention as tension as positive, compression negative, so this will the member forces in this will be written as this. For the equilibrium, to satisfy the equilibrium in the member, this should be equal to minus of this. So this will give us the member force. So in order to find out the member force, what we have to find out is only this thing for truss. Okay. So let us do that. So this equation already we know, written in terms of with respect to local coordinate system, and now this is the global coordinate system. All the information we have from the solution, whether it is displacement, forces, all the information we have with respect to the global coordinate system. Now we have seen, in order to find out the member forces, if we find out Q3 bar, which is the force with respect to the local coordinate system, we can find out the member forces. Now what we have to do is, whatever information we have with respect to the global coordinate system, that information needs to be projected on the local coordinate system to determine the member forces. How it is to be done? So we know that displacement can be displacement is related, the local coordinate system and the global coordinate system displacement is related like this. Okay. Now if we do that, so from this equation, from this equation, we will see that Q3 can be written as this. Okay, and U1 bar and U3 bar are the displacement with respect to local coordinate system, but this displacement now can be determined through this transformation, because we know the deformation with displacement with respect to global coordinate system. So if we do that, so this will be, if we substitute Q1 bar and Q3 bar from this equation, from this transformation equation, if we substitute that, we have this. Now next, if we substitute the for this member number 1, if we substitute alpha and U5, U6, 0 we have seen, and U1, U2 if we substitute, these become and then finally, finally this will be our the member force in this member number 1 or element number 1. Similar exercise we can do for other 2 elements to find out the forces in those elements as well. And if we do this similar exercise, this will be more or less our member forces. These are the reactions, displacement already we have determined, and these will be the member forces. Now you can compare with this truss is a statically determinate truss. You know how to solve statically determinate truss. You have studied several methods in structural analysis. You find out the solution from structural analysis and compare that solution with this solution, and then see where this solution stands. Okay, so this is called element force diagram. Now, so next class what we do is the objective of this entire exercise has not been to solve this particular truss. This is so simple truss, we don't need really finite element method to solve this truss. The method you have studied in structural analysis is more than enough to get the solution. But we have done it. We have done it 2 reasons: because it is simple, so that the manual calculation is possible, and through this process we understand, we comprehend the various steps involved in finite element method. Now next class what we do is, next class we'll see if it has to be done through a computer code, then how the computer code can be written, what are the different parts in the code. But then one thing we need to revisit before we start writing that code is determining the global stiffness matrix. You see here how we determine the global stiffness matrix. We determine through satisfying the equilibrium equation. Now we will see, is there any other way, if we translate the same thing into, if we have to translate the same thing into an algorithm for the stiffness, assembly of stiffness, how it is to be done. We will discuss that and then write the code and then solve slightly bigger problem. With this, let us stop here today. See you in the next class. Thank you.